In this video, I'm going to fit polynomials of degree 1 up to 6 to the data which is appearing on the screen there. And I'm going to fit those polynomials using Excel. The version of Excel that I'm using is 16.79.1. So the first step there, I'll go on and enter my data. So I'll put on my X, then I'll put on my Y, then put the values of the X and the Y. So I've now entered the values of the X and the Y. And the next step is now to highlight those values. So I click on this cell and then highlight all those values there that I've entered the values here. Then I'll go on where it says insert here. Click on insert. Then on insert, I'll go where we have the charts here. Then we look at the point where we have this scatter plot. So I'll click on the scatter plot, then go on and click on this part here where we have the scatter. So what we have there is this is the scatter plot of the given data that we have. But what we want is to fit polynomials to this given data. So what I'll do is I'll go to the top left hand corner on this part which is saying add chart element. So on add chart element, I'll click the drop down. I'll go where it says trend line. So on trend line, we have none here, or we have a linear. For linear, that's a first order polynomial. So that will be a polynomial with a degree 1. But for the other ones, degree 2, 3, 4, 5, up to the 6 that we want, I would have to move to where we're having more trend line options. So I'll go on and click here. And on the right, we would see that we have the first one there, which is clicked here. That's the linear. So the linear is corresponding to a polynomial degree 1. So that's the first that we need, polynomial degree 1. But what we now have to do is we have to go on and select the equation. If you want to show it on screen, I'll click here where it says display equation on chart. So I'll click here and we have the equation for the first order polynomial is y is equals to 0.5688x plus 0.9982. That's the line of best fit when you are looking at a polynomial of degree 1. If we look at again on the right hand side on this part here, you can see that there is a part which is saying display r squared value. The r squared is the coefficient of determination. It shows how well the data fit the regression model. So if I just click on this, it will show the r squared. It's giving it as 0.8269. I can just move it a bit upwards here so that it's not obscured by the line. So the r squared there is coming out as 0.8269. Ideally, an r square which is closer to 1 is the one which is preferred. So if the r square is closer to 1, we'll be saying that the data fits the regression model well. So what we are having here, that's the polynomial of degree 1. So if we want a polynomial of degree 2, we have to go to where it says polynomial here. So I'll click here, polynomial, and it's now indicating polynomial order 2. So we are saying the degree of the polynomial there is a 2, and I can go on and click where it says display equation so that it displays our equation there is 0.0617 x squared plus 1.203x plus 0.058. So that's the equation when you are looking at a polynomial of degree 2. And we can have our r square there, and we have the r square is 0.8798. As you can see, the r square has improved a little bit. So this is order 2, and we can check for order 3. You can just go on and check here. Click the up arrow so that it changes to 3. So we have for order 3 now. The equation now is 0.022x cubed minus 0.4005x squared plus 0.6138x minus 1.4158. And the r squared is now increased to 0.9135. For a polynomial of degree 4, I just click on the up arrow here. So we increase it to 4, and we are now having a polynomial of degree 4 here. So that's the equation there, 0.0101 x to the power 4 and lower other terms here. And the r square is 0.9414. And for the polynomial of degree 5 is this one here. And we are having the equation now is minus 0.0626 x to the power 5 plus some lower order terms there. And for the last one, we are having the polynomial of degree 6. I can just change this to put a 6 here. And now we have a 6. So in this case now, we are having our polynomial is minus 0.055 x to the power 6 plus some lower order terms. And what we can see now here is the r square here is equals to 1. It's saying it's almost a perfect fit. What you are seeing there is the line passes through all the points. So to some extent we can say that it is the best fit. But sometimes the best fit is determined by other conditions like the physical interpretation of the data that you are modeling. So for example, in this case, if we try to forecast forward, for example, if I say a period, and if I change to a period of, say, 3 periods ahead, and I press the return key, you see that the forecasted value here is in the negatives here, close just about minus 550, somewhere there. As x increases, we are having y, the forecasted value using a polynomial of order 6 there is giving us a negative value. But in engineering, there are some cases where the negative value for the variable y don't make sense. So if you are modeling something which does not have negative value, and you are modeling it with a 6th order polynomial like this one, which will give negative values for larger values of x, that means this model would not be appropriate, although it has an r square which is 1. But this physical interpretation there will not be the appropriate one for the situation at hand. So when you are fitting these models, of course, look at the r square, but also consider the physical interpretation of the data that you are looking at.